This is lesson 3.4, and obviously we are looking at applications of determinants here, as the title suggests. And we're going to look at three different ideas in this lesson. We're going to start by looking at what's called the adjoint of a matrix and how we use the adjoint to find the inverse of the matrix. And this is actually one of our learning objectives for the course. The second thing we're going to look at is what is called Cramer's rule. And this is, I think, kind of a smooth, if I can say the word elegant way of solving a system of linear equations. And the third thing we're going to look at is how to find the area of a triangle given the vertices of the triangle as ordered pairs. Now, there are a number of other applications in this section, and you might find some of those interesting. So I would encourage you, when we're done with this, to go through the book and just kind of look at some of those other examples. The one thing I'll say, and why I'm not going to go through those examples or those applications, is that when we go through the area of a triangle application, the others in the book follow a fairly similar pattern, enough so that I think if you understand how to find the area of a triangle, you would be able to apply some of those processes to the other applications. And so if you are interested in looking at those and trying those, you should be able to handle that once we've gone through this lesson. So with that, let's go ahead and get started with this whole idea of an adjoint of a matrix and how we use that to find the inverse. So to talk about the adjoint, we need to kind of step back for a minute and talk about cofactors. So if you remember, we talked about cofactors and minors, and we use the cofactors to get the determinant of the matrix. Now, we haven't really hit on this at all, but if I were to take a matrix and I found all of its cofactors, so I took every entry, found the cofactor of each entry, and made a matrix of that, we would call it exactly that. We call it a matrix of cofactors of A. And basically what that would look like is I would have an entry that would correspond to each entry in my original matrix A, but instead of the entry for A, we'd have the cofactor for that entry. Crystal clear, I hope. So idea is that as we go along here, we're getting all these cofactors, and I'm just going to kind of cut to the chase here, and we get down to our n by n, and this is our cofactor matrix. Why this is important is because, again, we're talking about the adjoint of a matrix, and the adjoint of a matrix is nothing more than this matrix transposed. Okay, so the transpose of this matrix is the adjoint of A. And we just write adjoint ADJ of A. That's how we symbolize it. So that's what an adjoint is. Adjoint is simply taking the matrix of all of the cofactors, transposing it, and you have the adjoint. Fabulous. Why in the world would we need an adjoint? What does this thing actually do? Well, that gets into finding the inverse now. So if I have this square matrix that's invertible, then I can find its inverse. And we've talked obviously about how to find the inverse before using the Gauss-Jordan elimination method. This provides another way of finding the inverse. And basically what we do is we take 1 divided by the determinant of A. So we do also need to find the determinant. And we multiply it by that adjoint matrix, by the adjoint of A. Okay. So let's just stop for a minute and kind of break down this formula a little bit and talk about exactly what that means for finding the inverse. So we know that to get the adjoint, we need to get the cofactor matrix, then we transpose it. To get the cofactor matrix, we need to go through every single entry, find the determinant for that entry, and then switch the sign. Remember, switching that sign based on where it is. So either making it, switching it to positive or negative, or leaving it as it is, based on its position. So we do that, we create the matrix, we transpose it, and then we also have to find the determinants, which again is taking then each entry in A times each of the cofactors, adding all those together to get the determinant. So bottom line is, if you really stop to think about this process, now for a 2x2, a 3x3, not a big deal, but you get into a 4x4, a 5x5, 6x6, it becomes a pretty daunting task. It's a lot of work to use this method. Generally speaking, you are far better off just using Gauss-Jordan elimination. So why this? What's the purpose of this then? Well, bottom line is it gives us an actual concrete formula for the inverse of a matrix. Gauss-Jordan doesn't actually give us a formula. It just gives us a method for how to find the inverse, but there's no actual formula attached to it. So this actually defines for us in another way what an inverse of a matrix is. The other thing is if you have any experience at all in any kind of programming, computer programming or anything like that, if I had the choice, just in my limited past experience, if I had the choice between writing a program that used Gauss-Jordan or using this, I'd much rather use this. This to me feels much more concrete, much more approachable, I guess is the word I would use, where I could see how to program finding the adjoint of a matrix versus trying to teach a computer how to do row operations to get that reduced row echelon form. So that would be the other reason is personally, and maybe I'm wrong, but personally I think that this is a more straightforward way to actually program and find the inverse. So with that, let's go ahead and kind of put this into a little more concrete terms and actually find the inverse then using that adjoint. So we're going to take matrix A here. We've got a 3 by 3 obviously. And we're going to start by finding that coefficient matrix. Now again, remember that with the cofactor matrix, remember that with the cofactors, where the position of that entry is determines whether we change the sign or not. So I'm going to just very, very quickly make for myself kind of a reminder that based on where we are in the matrix, I've got to remember to change the sign. Okay. So to find the cofactor matrix, we're going to go through each entry. We're going to cross off the row and column that entry is in, and then find the determinant of what's left. And again, for a 3 by 3, that's not actually too bad of a process. So if I go up to A, and I'll just kind of do this for this one, if I cross off the row and column, I look at the 4 remaining entries, I find the determinant. So in this case, -2 by times 0, multiplying the diagonals, 4 times 0, and I subtract. 0 minus 0 is 0. All right, so if I keep going across to 2, now I've got 1, 0, 3, 0 left. 1 times 0, 3 times 0, 0 minus 0 is 0 again. Going to -1, 4 minus a -6 is 4 plus 6, or 10. That stays the same. That's that positive, so we're going to keep it as 10. Going to row 2, crossing off the row and column where 1 is in, I would have 2 times 0, 4 times -1 is 0 minus 4 is a positive 4. But remember, I've got to change that sign to a -4. Going to the middle, I would have 0 minus a -3 is positive 3, and that stays positive. 0 would have 12 minus 6 is 6. That changes, did I do that right? Yeah, 12 minus 6 is 6, and then that stays negative, or that changes to negative. And then bottom row, we'd have, for 3, we'd have 0 minus 2 is -2, and that's going to stay -2. The 4, we'd have 0 minus a -1 is positive 1, but that changes back to a -1. And then finally, the lower corner we cross off, and we've got -6 minus 2 is -8, and that stays at -8. Okay. Not too bad, and obviously I talked it through. If I hadn't talked it through and just kind of did it mentally and written it down, it wouldn't have taken that long. So not too bad. But now we're going to use that cofactor matrix to find the adjoint of A. And again, the adjoint of A in this case is simply the transpose of that matrix. All right, so again, rows become columns, columns become rows. So 0, 0, 10, that row becomes the first column. Second row becomes the second column, -4, 3, -6. And the last row becomes the last column, -2, -1, and -8. So that's our adjoint. All right. Finally, we have to find the determinant of A before we can put this all into the formula and get our inverse. Now remember, with the determinant, you pick one row or one column and you multiply the entries of that row or column by the cofactors. So by obviously being strategic here, We can make this a light work for ourselves. If I choose in matrix A to just focus on that last column, there's 2 zeros there. And remember, where there's zeros, we don't have to worry about that finding the determinant. I just have to focus, in this case, on that -1. So in this case, we take -1, we take that entry, and then again, we either by looking at where the position is in the matrix, or taking -1 to the power of the rows plus the columns. So it's the first row, third column. So it's a power of 4, which makes it the sign the same, positive, which again in our matrix is positive. And then we multiply that by the cofactor, which is 10. So our determinant is -10. So again, for this problem, not too bad. Larger matrix, no zeros, could be a little more work. So finally, now that we have the adjoint, we have the determinant. Again, now we can find the inverse by just plugging everything in. We're going to take 1 divided by the determinant and then multiply that by the adjoint. So our inverse matrix is the 1 divided by -10, or -1/10, and then times the, in fact, I'm just going to write it this way, times the adjoint of A. And that's going to give us then the matrix 0. -4 over -10 is 2/5. And then we've got 1/5. Second row, again, we'll have 0. And then -3/10. Positive 1/10. And then we've got down in the bottom row, we'd have 10 over -10 is a -1. -6 over -10 is 3/5. And -8 over -10 is a positive 4/5. So that is our inverse matrix, and that's how we use the adjoint to find that. So hopefully that makes sense. If you've got any questions, obviously, as always, let me know. But let's move on then to the next idea, which is Cramer's rule. And as I mentioned earlier, Cramer's rule is a method for finding or for solving a system of linear equations. And again, I think this is a really kind of slick process. We know how to, again, solve a system algebraically. We know how to solve it using Gauss-Jordan elimination. I actually think this might even be better than those methods, depending on the matrix or the system that you've got. But very simple. I'm gonna just do this, and then we're gonna backtrack, and I'm gonna show you kind of what I did. So I'm gonna, to find x1, I'm gonna take 13, and see if you can kind of figure out what I'm doing here. I'm gonna take 13 times -1 minus -23 times 3. And I'm going to divide that by 2 times -1 minus 4 times 3. And if I simplify that, I've got a -13 plus 69 is going to be 56. In the bottom, I've got -2 minus 12 is -14, which gives me a -4. That's the value of x1. Okay? All right, let's try x2. Now, if you pay attention here, because as I go through x2, it's going to look similar, but there is a slight difference. So again, let's see if you kind of catch what's going on here. I'm going to take 2 times -23 minus 4 times 13, and I'm going to divide that by 2 times -1 minus 4 times 3. So again, in the top, -46 minus 52 more. Really stretching my mental math here. -98 divided by -14, which is a +7. So that's my solution. x1 is -4, x2 is +7. Now, if you kind of noticed, hopefully kind of saw some of the, almost what I call cross-multiplying between the two different equations to get the different parts, the numerator and denominator of those fractions. Let me kind of break this down for you in case you didn't quite see what happened there. So let's generalize this. I'm going to take just kind of consider the coefficients here, the numbers, and not worry about the actual variables. So I'm just going to do a11 plus a12 equals b1, a21 plus a22 equals b2. Okay. So obviously imagine that there's an x and a y or an x1, x2 attached to those a values. But just focusing on those as numbers, what we're going to do is we're going to find what's called the determinant of a1. In other words, what I'm going to do is I'm going to take the coefficient matrix. So if I ignore the b's for a minute, I take the coefficient matrix a11, a12, a21, a22. And for the determinant of a1, I'm going to replace that first column with the b values. So I'm going to find the determinant using b1, a12, and b2, a22. Okay, so go back to our example then. Basically, I'm taking then the b values and the second coefficient, so think of that as a -1 in front there, and that's what I multiplied. I took the 13 times the -1 minus the 3 times the -23, okay? Then in the bottom, it's just the determinant itself. If you look at the coefficient matrix, the 2, 3, the 4, -1, that is how I got the bottom, is just finding the determinant of that. So then A2, we're going to find another matrix. So to find X2, we're going to take the determinant of what we call A2. And here then, I'm going to take, again, this coefficient matrix, but now I'm going to replace the second column with the B values. So I'm going to take A11, A21, B1, B2, and find the determinant of that, which would be the numerator then for X2. Okay? So then X1 is just the determinant of A1 divided by the determinant of A. X2 is the determinant of A2 divided by the determinant of A. And we can keep going then. So if I have 3 equations with 3 unknowns, I would just do the same thing. I would just have X3 is the determinant of A3 over the determinant of A, where now I'm replacing the third column with the B values, and so on and so forth. So that's how we use this idea of Cramer's rule to find or to solve a system of equations. So let's go ahead and let's do one more example, and we'll do a 3x3 for this one, or a 3 equation system. So for this then, let's actually start by finding the determinant of A. So that's just taking the coefficient matrix for the left side. So we're going to have 2, 3, -1, 3, -2, 5, 1, 1, -1. So again, to find the determinant, we pick a row or a column. We have to multiply the entry by either a positive or -1, and then times the cofactor. Okay, so I think looking at this, I'm going to pick the bottom row just because it's all ones, and that'll just be easy to multiply out. So I'm going to take 1 times the, or in this case, times a +1, right? Because it's positive, negative, positive, so it's a positive location. And then times the determinants, so 15 minus 2, right? I'm looking right here. 15 minus 2 is 13. And then plus, so now we go to the 1, and so 1 times, now that's in the negative position, so I have to multiply by a -1. And then I've got 10 minus a -3 is 10 plus 3, or 13 again. Running out of room here. And then plus, now the last entry, -1, that's in the positive position. So obviously you don't need to write these ones, but just so you remember that they're there. And then for this one, we have -4 minus 9 is a -13. All right, so that gives me 13 minus 13 plus 13 is a 13. So that's my determinant. That's the determinant of A. So now to solve for X, Y, and Z, this is where we're going to kind of set up that determinant of A1, A2, and A3. So starting with X, we're going to replace, and I'm just going to set this up as a determinant with the matrix. We're going to take the first column of A. So I'm looking over here now at this just to kind of see this. I'm going to replace this first column, 2, 3, 1, with 7, 4, 3. So this is 7, 4, 3. And then the rest of it stays the same. 3, negative 2, 1, negative 1, 5, negative 1. And we're going to divide that by that determinant that we just found, the 13. Okay. Now, before I get into finding the actual determinant of that numerator, remember that we can manipulate the matrix before we do this. We can actually do row addition and things like that to change it. So in this case, what I'm going to do is I'm going to actually take the bottom row times negative 1. Let me kind of write this here. I'm going to take that bottom row times negative 1 and add it to row 1. Now, it doesn't make a huge difference. What happens is I take negative 3 plus 7. That's going to be a 4. Negative 1 plus 3 is a 2. And then positive 1 plus negative 1 is 0. And very simply what that does now is it just makes my work a little bit easier, because now I don't have to do 3 terms, because remember, where there's a 0, I don't have to deal with that. I only have to look at the first 2 terms. So kind of watch for those things that you can do to make life just a little bit easier for yourself as you go through these. So again, we're finding the determinants. So 4 times, in this case, it's in the positive position, and then times 2 minus 5 is negative 3. And then plus 2, that's in the negative position, so times negative 1. And then its determinant would be a negative 4 minus 15 is negative 19, all over 13. And so I've got negative 12, right? This is negative 12. This is positive 38. So that's going to give me a positive 26 divided by 13 is 2. So x is 2. And now we're going to do the same thing for y and z. And I'm actually going to walk through both of these in detail just like I did with that one. So y. Now I'm looking at the second column. I'm replacing that second column up here with the 7, 4, 3. So I'm going to write 2, 3, 1, 7, 4, 3, negative 1, 5, negative 1. And again, all over the determinant of A. Now, again, I'm going to do the same thing I did before. I'm going to add the opposite of R3 to R1 just to make that a little bit easier to find the determinants. So negative 1 plus 2 is 1. Negative 3 plus 7 is 4. Positive 1 plus negative 1 is 0. All right, so using that top row again, we've got 1 times negative 4 minus 15 is negative 19. And then plus 4 times negative 1 times negative 3 minus 5 is negative 8. All over 13. So we have negative 19 plus 32 is going to be a positive 13 over 13. So y is 1. All right, and then finally z. So same thing. Now we are going to take that third row and replace it with 7, 4, 3. And so we've got 2, 3, 1, 3, negative 2, 1, and then 7, 4, 3, all over 13. All right, so again, let's see. This time I think I'll take the opposite of, or 2 times the opposite of row 3 and add it to row 1. So then negative 2 plus 2 is 0. Negative 2 plus 3 is 1. And negative 6 plus 7 is 1. That makes for really nice numbers on this last one. And so we've got, again, we can skip the 0. We've got 1 times negative 1 times 9 minus 4 is 5. And then plus 1 times 3 minus a negative 2. 3 plus 2 is 5. All over 13. And we've got negative 5 plus 5. That's just going to give us 0. So that is your solution. We've got x equals 2, y equals 1, and z equals 0. So, you know, again, obviously I talked through it, so it took a little more time to do and things like that. But, you know, I think it's a pretty nice way to find a solution to a system like this. You know, certainly if you've got really good mental math and you can kind of whip through some of those calculations quickly, it may be actually more efficient than taking the two equations to break down to a system of two equations, two unknowns, and then solving that and then backtracking up. So maybe a horse apiece, I'm not sure, but another, I think, really nice, elegant way to solve a system. All right, let's go ahead and go to our last one, which is area of a triangle. So basically what we've got here is that the area of a triangle in two-dimensional space, so in the XY plane, with vertices XY, X1, Y1, X2, Y2, and X3, Y3 is given by the following. So the area is plus or minus 1/2 times the determinant of X1, Y1, 1, X2, Y2, 1, and X3, Y3, 1. So very, very simply, if you think about even like what the area formula is for a triangle that you probably learned back in geometry, if not earlier, right? Area of a triangle, 1/2 base times height. So basically what you've got is that plus or minus 1/2 right in there, and then just time the determinant of that matrix, where you're just taking those ordered pairs, attaching on a 1 in a third column, and we're just going to find the determinant and solve. Now, the only thing I want to just mention here is that plus or minus 1/2. This plus or minus is obviously where there's not two answers. You don't have a positive and a negative area. All that's there is just saying if you would get a negative determinant, you just make it positive. If it's a positive determinant, you keep it positive. So that's all that plus or minus is there for, is just to basically make the positive area for the triangle. All right, so let's go ahead then and do an example of this and wrap up this lesson. So find the area of a triangle with vertices 2, 1, 4, 8, and 7, 3. So very, very simply, the area is, again, that kind of plus or minus 1/2. Determinant of 2, 1, 0, 1, 4, 8, 1, and 7, 3, 1. All right, so again, I think here I'm just going to burn through this. I'm not going to do try to get a 0 in there. I'm just going to take that last column. We've got plus or minus 1/2. And then we've got for 1, that's in the positive position. 12 minus 56 is negative 44. And then plus 1 times a negative 1, that's in the negative position. And then we've got 6 minus 7 is another negative 1. And then plus 1 times positive 1. And 16 minus 4 is 12. All right, so now it's just a matter of simplifying this down. Plus or minus 1/2. We've got negative 44 plus 1 plus 12, which is plus or minus 1/2. Let's see, we've got negative 44 plus 12 is negative 32, plus 1 is negative 31. So again, this basically just says make this positive. So it's a half of 31. So it's 31 halves, or 15.5 for the area of your triangle. So kind of a cool little way to find the area if you've got the 3 vertices. Think back to your geometry days again, or trigonometry days, whatever the case may be, where you're finding the area using law of sines or law of cosines, or some kind of crazy thing like that. So a pretty efficient way if you know those vertices. Like I said, the book has a lot of other examples in it, a lot of other applications in it. It goes through finding the line through 2 points, a plane through 3 points, area of a tetrahedron, things like that. But all of those do kind of follow, again, this similar idea to what we just did with the area of a triangle. So you should be able to kind of go through and follow those if you're interested in looking at those. So that's it for this lesson. As always, reach out if you've got any questions. I'm happy to help you out. Otherwise, I'll see you in the next lesson.